Hello, let's go through PaLI-3, Vision Language Models, Smaller, Faster, Stronger. Recently, we read PaLI, which was the Pathways Language Image Model. This is PaLI-3, so the next iteration of that. And this is a pretty impressive paper in that it created one of the main contributions is a model that is 10 times smaller than competitors, but performs just as well or better. So this is pretty cool. Now we're getting close to the actual state of the art with PaLI-Gemma. This is October 23, so less than a year old by now. And main contributions are, first, they discover something funny. So if you remember LIT, they argued that using a pre-trained image model that was pre-trained for classification and freezing it, and then training the language model to match that image model gives really good results. So that was the discovery that they made in LIT. And here they do something similar, but also something weird in that first they contrastively pre-train an image language model. So they have this WebLi dataset, which is really large scale, there's like, 10 billion or something example pairs, text image pairs. And it's a bit noisy because it's, scraped from the internet. Not the highest quality data, but it's good enough, and there's just a lot of it. And they use it to pre-train a vision language model in the standard way. So they don't start with a pre-trained model. They start with randomly initialized weights. They train the image language model together. Once they're done training, they take the image model, freeze the weights, and they throw away the language model. And then they take this contrastively pre-trained image model, and they take that as this new frozen image model for PaLI-3. And then they attach a fresh, randomly initialized language model, and then they do training, and that's how they get this really good performance. So it's just funny because now they discovered that pre-trained classification model was better than training from scratch, but now they discovered that actually training from scratch and then freezing it and then training the language model on top of it is even better. So that's what they say here. That's the first contribution. We compare classification pre-trained VIT models to contrastively pre-trained SIGLIP models using the PaLI framework. So SIGLIP is just, it's an important finding, but it was an optimization of the loss computation. And that's where they also did, like we talked about it, so I'm going to summarize. So they compare classification pre-trained VIT models to contrastively pre-trained SIGLIP models. Using the PaLI framework, we find that the contrastively pre-trained models work significantly better for visually situated text understanding. And there are, I think, for pure image classification, the classification pre-trained model still works better, but it's a small difference. But the SIGLIP contrastively pre-trained model works much better across all the other tasks, generalizes much better. And they have state-of-the-art results, and it also generalizes on to video apparently, even though they didn't train on it. And they released this 2 billion parameter pre-trained SIGLIP model that they'd use as a base for frozen stuff here. So this is it. I mean, the architecture is kind of what you would expect. There's this frozen 2 billion vision model that takes an image, has this encoder that turns it into a bunch of tokens. Then they have a tokenizer that takes the query, so whatever you write, tokenizes it, and then they concatenate these two tokens together, and they feed it through this language model that is then trained. Actually, is it trained from scratch? No, I can't remember what is trained from scratch or pre-trained, but I think it's trained from scratch. So it's an encoder decoder model, and that gives it the final answer. So that is kind of all pretty standard. Here they show the different stages of training. And what else? Oh yeah, they also find that for some tasks it's much better to have higher resolutions. So instead of 224 squared, they go to 812 or 1064 squared. And it makes sense, especially for like document understanding. If you have lots of text, when you scale everything down to 224 squared, the text would just be impossible to read even for a human. So they do another round of training on high resolution images to make that possible. And they also then take this model and then specialize it to certain tasks by fine-tuning it for specific data. And then they go through a bunch of experiments showing performance improvements. So that is the paper. Thanks.